In this paper, we present an interactive perceptual rendering pipeline using contrast and spatial masking. We develop a new algorithm which can efficiently determine inter-object visual masking due to occlusion or shadows, and use of masking to control level of detail. Consider this example. The shadows from the upper window with bars mask the details of the gargoyle. Our approach can detect this efficiently. If we have a high-frequency shadow, shown here, the level of detail is low. When we decrease the shadow frequency, masking becomes less pronounced, and our method increases the level of detail. Our solution involves dividing the scene into layers and using threshold maps to predict masking in images. For this scene, we have the following layers. We also render the background. The layers are rendered to separate render targets and stored as textures on the GPU. We want to determine masking for objects in layer 1, for example, so we can choose a rendering parameter such as the level of detail. To choose such a parameter for an object in layer 1, we need to ignore it so that it will not interfere with decisions concerning itself. To do this, we combine layers 0, 2, and 3, omitting layer 1 but including the background. We can then compute the threshold map for this layer. As we can see, visual masking is predicted to be high in the regions with many objects or in regions with shadows. We use this framework to control the level of detail. In the following step, we render the objects of layer 1 at a high level of detail. We compute the difference of each pixel, for example the dinosaur, with a current level of detail. We then compare the differences with the threshold. We send the number of pixels with a difference higher than the threshold back to the CPU with occlusion queries. If the number of pixels with difference above the threshold is greater than the upper threshold TU, we increase the level of detail. If the number is less than TU and greater than TL, we maintain this level of detail. Else, if the number is less than TL, we decrease the level of detail. To validate our algorithm, we performed a perceptual user study. The idea is to see how often our approach correctly predicts whether a difference is visible or not. The user is presented with two sequences, side by side. After the first presentation, the user is asked whether she can see the difference and can answer yes or no. For 11 subjects and 12 configurations, our study shows that our algorithm predicts the correct answer 65% of the time. We now show results of our approach. In what follows, we alternate our approach with the standard distance-based LOD mechanism running at the same frame rate as our approach. In this sequence, we have a house with many complex objects. Note in particular the statues inside the doorways. Similarly, we compare our approach to distance-based LOD. We can see that for equivalent frame rates, our approach will maintain quality appropriately, for example for the statues in the doorways. The distance-based LOD algorithm does not maintain the appropriate LOD for the statues, and the difference is visible. From highest to lowest LOD, we have red, blue, green, yellow, and white boxes. Our approach chooses lower levels of detail than distance-based LOD in regions with masking, but not for the statues, for example. Our next scene is an outdoors forest scene. Similarly, we compare our approach to distance-based LOD. For the large raptors chasing the smaller dinosaurs, our approach chooses higher levels of detail, maintaining better visual quality.